Chapter 3, Exercise 5. Note that if real sequences Sn and Tn are such that this and that for all large enough n, then S less than or equal to T. Consider three cases: when this or that, when this or that, and when both this and this are finite. Use characterizations of the upper limit from Theorem 317. Auxiliary statement. Assume that Sn and Tn are real sequences such that this and there exists an integer n such that n greater than or equal to n implies this. Then S less than or equal to T. If S equals minus infinity or T equals positive infinity, then this statement is obviously true. Consider the case when S equals positive infinity. By definition, for any real number m, there exists an integer n1 such that this implies that. If we take this, then this implies this. It follows that t equals plus infinity equals s. Consider the case when t equals minus infinity. For any real number m, there is an integer n2 such that this implies that. If we take this, then this implies this. It follows that s equals minus infinity equals t. It remains to consider the case when s in R, t in R. Assume that s greater than t. Let epsilon equal this. By definition and by assumption, for all large enough n, we have Sn less than or equal to Tn, this. In this case, we have this, which is impossible. This proves the statement. Denote A equals this, B equals that. We need to prove that this. This will be done using characterization of the upper limit from Theorem 317 and the auxiliary statement. Case 1. Assume that A equals positive infinity. By assumption, B greater than negative infinity, and this. The case B equals positive infinity follows by symmetry. Case 2. Assume that A equals minus infinity. By assumption, B less than positive infinity, and this. We need to show that this. Let M in R be given. Fix a real number y greater than b. There are integers n1 and 2 such that this implies that and that implies this. Theorem 317b. If n greater than or equal to maximum of n1 or n2, then this. This shows that this, in particular this, the case b equals minus infinity follows by symmetry. Case 3. Assume that A in R, B in R. Consider a real number x greater than A and B. Since x minus b greater than A, there is a real number y such that this. Since b less than x minus y, there is a real number z such that this. Arguing, as in case 2, we can find an integer n such that n greater than n implies this and that. So n greater than n implies this. Assume that S is a limit of a subsequence, here. For a large enough indices I, we have ni greater than or equal to n and this. According to the auxiliary statement, this, all subsequential limits of this are less than x, in particular this. The later inequality is proved for any real x greater than a plus b. In particular, inequality here leads to a contradiction. It follows that this. The result of this exercise tells us that the upper limits has the property known as sublinearity. The proved inequality can be strict. As an example, consider sequences an equals this, bn equals that. We have this and this. However, an plus bn equals 0 and the following. A similar result holds for the lower limits, here. Provided the sum on the right is not of the form infinity minus infinity or negative infinity plus infinity. The auxiliary statement is an important property that justifies passing to limits in inequalities. Thanks for watching.